Next, we'll turn our attention to the skies and beyond, and our second lecture, The Next Generation of Science and Threats from Space. In recent years, space exploration has taken off like never before. Today, we'll explore NASA's latest missions and the big questions they aim to answer. We'll also dive into the work being done to detect killer asteroids and how we can defend our planet. Finally, we'll look at the growing field of space defense and the rise of the Space Force. And to help us explore this story today, I'm honored to introduce someone who knows space well, Professor Dan Scolnic. Professor Scolnic is an associate professor of physics here at Duke University, who leads a cutting-edge research group that uses world-class telescopes to measure the expansion history of the universe. His work aims to answer some of the most fundamental questions we can ask. What is the universe made of? How did we get here? Recognized as a leader in the field of cosmology, Professor Scolnic has received numerous prestigious fellowships and is one of the highest cited scientists in the field of space science today. Please join me in welcoming Professor Dan Scolnic.
Hi, everyone. Thank you for that great introduction. Thanks to everyone for being here. I just want to say, first of all, that if I look tired, it's because I stayed up to watch the whole basketball game last night, and then I could not sleep afterwards because it was so stressful. But yes, the game that starts in an hour. Okay, so I am going to be talking about space in terms of exploration and now defense. And this talk is the next generation of science and threats from space. And I say until about a year or so ago, I was kind of a pure academic. I'm just trying to understand the biggest questions in the universe. But as more industry goes into space and as weapons are starting to go into space, there's this tidal wave that's kind of pulling me and a number of others in this direction. I want to talk a little bit about what that journey looks like, and I think kind of what the future is going to look like in both good and scary ways. So I, last year, was selected to be part of the Defense Study Science Group. The military chooses about 12 professors every 2 years that represent all the scientific disciplines. We go and we visit military bases and we talk to generals about what are their problems, how are they going to need science and technology in the future. And to do this, I had to get my secret security clearance. And I don't know if anyone has gone through this experience, but it's an extremely personal experience. These people know everything about you, credit card statements, any weird red flag, and they will ask questions about your marriage and your kids and how good of a father you are, looking to see if you could be blackmailed in any way. And it's very strange. And at the end, the conclusion from my security clearance interviewer was, "Your life is very boring," but that's actually a good thing. So I thought I could tell you a little bit about my boring life, and you could see how this kind of pulled me into some of this stuff. So I have a wife and 2 kids, and my older daughter Talia. Actually, what claim that she has is that. So what I work on, and we'll talk about in just a few moments, is I try to find exploding stars called supernovae, and these are explosions that are billions times billions times billions more than an atomic bomb. So the biggest explosion in the whole universe. They're happening billions of light years away. And we use this technique called image subtraction, where we take pictures of the sky. So that's like the before. This is of a galaxy. And then we keep every few nights taking pictures of the same part of the sky. And then we subtract the images. So we're basically playing find the difference, but using machine learning and some fancy tools. And that last column on the right, that's the subtracted column. And what I circled in green, that's an exploding star called a supernova. And my team was trying to find the oldest, furthest supernova that have ever taken place. And we had a rule, because these are so rare to find them, that if you happen to have a kid at the time that a supernova went off, you get to name the supernova after your child. So this one here is Supernova Talia, discovered January 2015. Now, you may think this makes me a pretty amazing father. And I would have thought so too. The problem was I then had a second daughter, and the program ended. So now I have one daughter with a supernova and another daughter with absolutely nothing. Okay. So bucket 2 is basketball. This is me with some of my grad students. I actually taught the physics of sports here at Duke. I now actually help co-lead a house course called Basketball Analytics that undergrads really lead, and then space research. And this has kind of blossomed in a lot of interesting directions. Okay, now I want to give one kind of takeaway about the state of cosmology before I move more terrestrial. And that is that we know that everything that you learned in science class as a kid, people, planets, stars, galaxies, everything that you could see makes up 5% of the universe. The rest of the universe are things that we can't see. There's something called dark energy that makes up 70% of the universe, and something called dark matter that makes up 25% of the universe. We don't know what those things are, and a lot of our big experiments now are trying to figure that out. We could tell that things are getting pushed away from the dark energy and getting pulled together by the dark matter, but we don't understand them. So the kind of pinnacle of understanding of astrophysics and cosmology today is that we're at 5%. So we are currently kind of failing the exam, so to speak. Okay, now what my team does at Duke, we have found the most number of supernovae that kind of any group ever. And what we're trying to do is we're trying to find these explosions. When there's a star, what we call a white dwarf, which is what our sun's going to turn into when it dies, and if it can pull matter from another star, it'll explode. And this is this thing that is one of the biggest explosions in the universe. And it's so big that we can then see these explosions all the way across the universe. And that gives us kind of like a snapshot of what the universe looked like a long time ago. Okay, so the military has a number of satellites. And there's the NRO, which is the National Reconnaissance Office, that they make such better satellites than we could even use. They have a bunch sitting in a hangar. And at one time, someone realized that, hey, what if we donate this to NASA? Because this is more than NASA could ever afford. So that is now called the Nancy Grace Roman Space Telescope. It was a spy satellite that we have refurbished. It's about $3.5 billion worth of work. And this will be launching next year. And one of its great things is it'll be able to see lots and lots of these exploding stars, thousands of these supernovae, so we can measure how the universe looked like as it grew up. And just to kind of give you a sense of scale of this, so everyone probably knows the Hubble Space Telescope. This is the field of view of the Hubble Space Telescope. And to compare this to what I'm working on that will launch next year, you're going to see Hubble, and then this is Roman here. It's 100 times the field of view of Hubble. So all those pretty pictures that you've seen from the Hubble, we'll be able to do that 100 times faster, get 100 times more science. And this launches next year. It's a really amazing instrument, and it launches, we hope, kind of October 2026, which is like tomorrow in astronomy terms. It's very soon. So we're very nervous and excited. Okay, what this can do is this can find lots of these exploding stars. I'll show you a quick little movie of kind of how what this will look like. This is amplified, but you'll get a sense of it. This is that field of view of Roman, and we put this is during the holidays, so we put little music to this. This colleague, Michael Traxel, did this. And all those little dots, those are supernovae. We'll be able to measure each one and then see kind of what the universe looked like at that time to see how the universe has been expanding, and then try to understand what makes up the universe. Now, I want to try to tell you two techniques, since this is micro-learning lecture. I'm going to try to teach this to you. So we're going to go into professor mode for just 1 second. The first is parallax, and this is a really cool one just to do with your thumb. So if people don't mind trying this out with me, if you could put your hand over one of your eyes and stick out your thumb, and then move your hand back and forth, and look at the position of your thumb relative to the background. What you should see is that it seems like the thumb is moving, even though your thumb's not moving. Right? That is parallax. That is that you're changing the vantage point from your two different eyes. And if you happen to know the distance between your eyes, and you can measure that angle, then you could figure out the length of your arm. So it's a way to tell distances to things far away if you know some baseline and you can measure angles really well. This is what we utilize to measure things far away. We're looking when the Earth is on one side of the sun versus the other, and looking at differences in angles of stars to figure out how far away they are. The other is an idea called standard candles, which you could also understand from this room, which is that if you knew some lights where it had exactly the same wattage, came from the same factory, and you could see some look brighter than the others, you could tell this one must be this much closer than the other. So these are kind of the two main ideas. They're very practical, but this allows us to figure out how far away galaxies are that are billions of light years away. Now, when my team does this, we measure the expansion of the universe, and this is now called the Hubble tension. the expansion rate that we find of the universe is much faster than predicted. And this is big question of what's going on. Now, I kind of want to switch from this, from kind of cosmology, to say, well, how do we use this for something more terrestrial? Okay, now probably people saw this. This is just like a few weeks ago. Every few days, there's an announcement about this asteroid, 2024 YR4, and it was a 3% chance it was going to come and kill us all, and then a 2% chance and a 1% chance. Well, what was going on over those few weeks when everyone was going crazy? What was happening was that it is hard to figure out exactly what the orbit of that asteroid is. And what was hard about that is measuring the distance to that asteroid, because it's moving and it's coming at us. We have this good idea of how we can measure parallax. What we were doing before was trying to figure that out for galaxies billions of light years away. What if it's just thousands of miles away? Well, what we realize is that as the Earth rotates, then the position, just like kind of we're moving between our eyes, the position will change. And we could use that same signal to figure out the distance to the asteroid to then constrain its orbit and figure out whether it'll hit us. So we do the same thing. This is a work with one of my grad students, Marianne Fernandez, where we're using that technique, but now we're using the rotation of the Earth, and then we could figure out the distance to the asteroid. And this is what it looks like kind of in a science plot. Those wiggles just has a period of 1 day, because our Earth has a period of 1 day. And the size of those wiggles tells you about the distance to the asteroid. And it's a small signal, but we can measure it. And there's a great write-up about our work just last month about how we can more quickly and easily figure out if an asteroid is coming to kill us. I'll just kind of give one more example of this, about something even closer. And it's getting kind of more into my military work, which is that probably people saw in the news about drones over New Jersey. Now, that seemed weird, but that's going to be happening all the time, because about 15 drones are made each minute across the world. So the amount of stuff that's just going to be flying all over the place is really going to jump up, and you're just going to see this more and more and more, and it's a serious problem. Now, my team is working with this group at Harvard to try to detect these drones better, and we're using the same kinds of telescopes and the same kinds of image subtraction, and we're just trying to monitor the sky and say, is there anything flying over, and could that be a drone? Who do you alert about it? Should you shoot this down or not? And this is what our kind of first baby picture of a drone is 100 meters out. So we've been just flying drones over these new little telescopes using the same technology, but now for something just much closer. So I'll end it there, and I'll just say that kind of all these techniques that we've developed for astronomy are turning out to be very useful in terms of both national defense, but also planetary defense. And it's a really interesting time, but also a strange time, because it's hard to kind of predict how much is going into space and what we need to be doing about it. I'll end it there. If you have any questions kind of after this, you feel free to email me. Also, go do basketball. Thank you.